In the United States, the CDC estimates that up to 3% of children born each year will have a major structural birth defect that appears by their 6th birthday. The real contribution of environmental factors is unknown. Humans are exposed to hundreds, if not thousands, of natural and synthetic compounds with unknown or untested biological consequences. Our goal is to develop robust, in vitro, three-dimensional OCMs with adult human mesenchymal stem cells. So first, examine critical phenomena in embryonic limb development that may be targets of teratogens, and then to test their susceptibility to perturbation by known and unknown environmental toxicants. Skeletal abnormalities or dysplasias are among the most visible common birth defects. Up to 70% of abnormalities have an unknown etiology that's presumed to lie at the intersection of the genome with environmental influences. We're trying to model 3 different phases of limb development: chondrogenesis, hypertrophy, and joint segmentation, each with a unique in vitro model. Across the bottom of the figure are actual cultures of these 3 models using chick limb bud mesenchyme. They are fixed and stained with Alcian blue to reveal cartilage-specific sulfated proteoglycan deposition in the culture. The first critical question Project 2 has to answer is to what degree adult human mesenchymal stem cells can recapitulate developmental processes. Chondrogenic and hypertrophic cultures are sequential. Chondrogenesis is induced with TGF-beta3 in defined medium for 14 days, while hypertrophic cultures are initiated at day 10 of a chondrogenic culture, at which time triiodothyronine, or T3, replaces TGF-beta for the next 7 days of culture. Establishing the differentiation potential of the MSCs and testing both endpoint and non-invasive assays is tested in simple, multi-well cultures that are manually maintained and assayed. We refer to these cultures as version 1 of each OCM. The base system for these models is a 2 microliter droplet containing 40,000 cells that we seed upon polystyrene surfaces that we texturize and coat with extracellular matrix molecules. These cultures are currently being adapted to existing OCM bioreactors developed by Project 5. In preparation, we must determine flow rates and the ability of these cultures to be seeded and grown on porous membranes common to other OCMs in VPROMPT. For proof of concept, 3D printing was used to form a chamber 5 mm in diameter and 2 mm high, with a membrane bisecting the space in the horizontal plane. Seeding the culture and gelatin overlay is accomplished in an open format. Flow is applied to the cultures at 2 milliliters per day, or 1.3 microliters per minute. Viability and metabolism of the cultures is monitored through analysis of the conditioned medium. Differentiation can be monitored in situ through the use of tissue-specific promoters for reliable, validated markers of differentiation and hypertrophy, such as collagen-2 and MMP13, respectively. Our third OCM will model joint segmentation. In vitro models of joint segmentation currently do not exist. We hypothesize that joint segmentation can be initiated within a prechondrogenic model through flexion or mechanical stimulation and the addition of specific biochemical signals. We have seen evidence of joint-specific gene expression in mechanically stimulated cultures using chick embryonic limb mesenchyme, but further work will be required, especially in proving that adult human mesenchymal stem cells undergo such activity as well. For this project, we must develop joint segmentation models that are amenable to microscopy and microfluidics. The device involves motion of concentric rings to produce flexion at the center of a culture trough. Bioactivated hydrogels, comprised of natural and synthetic polymers, are loaded with MSCs and are polymerized in situ within the trough. Development of the motorized device is ongoing and is required before microfluidic adaptation of this OCM. excited about being a member of the VPROMPT project. In the coming year, we will characterize limb model development downstream of Project 4 Liver OCM, a critical organ to processing and possible bioactivation of chemicals harmful to the embryo. We hypothesize that placing the placental OCM between liver and limb will generate a more physiological model for the activation, transport, and absorption of chemicals to the embryo, thus allowing us to better predict teratogenicity of chemicals in our environment. These systems will be adapted to common platforms that can be controlled and analyzed robotically in a medium to high throughput format that will increase the rate and decrease the cost of testing, with the long-term goal of maintaining a cleaner, more healthy environment for ourselves and our children.